Okay, welcome back. With that review of p-n junctions, we're now ready to examine the bipolar transistor. So we discussed the injection currents in forward biased p-n junctions. We lower a barrier, we get electrons injected from the n side to the p side. We also lower the barrier to holes injected from the p side to the n side at the same time. So we have these two expressions for the electron and hole currents in a forward biased p-n junction. Okay, let's draw an energy band diagram for the heart of a bipolar transistor. This is an NPN transistor. We'll have a very heavily doped N-type emitter. That's what the N plus stands for. We'll have a less heavily doped P-type base and usually an even lighter doped N-type collector. If we draw an energy band diagram from the emitter through the base out the collector, you can see here's our N-type region, here's our P-type base. Notice it's still called a base, even though it's not, the transistor is not sitting on the base the way the first transistor was. And then we have an N-type collector and a very heavily doped subcollector to make good ohmic contact. If you look at this energy band diagram, it looks a lot like the energy band diagram for an N-channel MOSFET that we drew earlier in the course. In that case, we had an N-type source, we had a P-type channel, and we had an N-type drain. So these devices, their energy band diagrams look quite similar. That means their operating principles are, in fact, quite similar. Okay, so we're going to examine the operation of this NPN bipolar transistor. So this is a barrier-controlled device. So the way it's going to operate is that we will apply a positive voltage on the base with respect to the emitter, and that will pull down the energy barrier between the emitter and the base. At the same time, we are going to apply a reverse bias between the collector and the base. That means a positive voltage on the collector with respect to the P-type base. That'll pull the energy down and reverse bias that collector base junction. Okay, if we do that, this is the picture that we get. We have pulled down the base energy with a forward bias. We have then lowered the energy barrier for electrons to be injected from the emitter to the base. We have pulled the energies in the collector way down with a reverse bias. So now we have a lower energy barrier at the electron base junction. Electrons can be injected from the N side to the P side. They can diffuse across the P side, and then they can be swept by the high electric field and just flow downhill and out the collector contact. That's the basic principle of operation. That should remind you of the energy band view of an N-channel MOSFET. Now, there is a widely held view by people that bipolar transistors and MOSFETs are inherently different types of devices that operate on different principles. That, in fact, is not true. It's been understood for a long time. I can refer you to this very old paper from 1973, where it was pointed out that the insulated gate field effect transistor, what we now call a MOSFET, and the bipolar junction transistor operate on really the same physical principles. So this has been known for a long time, but the way it's presented in textbooks, probably the majority of people who work on transistors still don't appreciate the fact that these two different types of transistors operate on the same basic principles. So we are going to be thinking about this device biased in the forward active region. This is sort of like the saturation region of a MOSFET. In that region, we will forward bias the base emitter junction so that we inject electrons into the base, and we will reverse bias the base collector junction so that we collect the electrons that are injected. The current then that comes out, electrons will be injected into the base, diffuse across the base, and come out the collector. The current that comes out will be that electron injection current density multiplied by the area of the emitter base junction, which is doing the injecting. Now, at the same time, we have these holes being injected from the base into the emitter. The holes have to be replenished. Holes have to flow in the base contact. That gives us a base current. And again, the base current is given by this simple expression that we developed earlier for the whole current density multiplied by the area of the emitter-base junction, which is where the injection is occurring. So we have these simple expressions for the collector and base current. Okay. All right. And Kirchhoff's current law tells us if we have a base current coming in the base contact, a collector current coming in the collector contact, then the sum of the two go out the emitter contact. That's just Kirchhoff's current law. Now, you'll sometimes hear that what makes the bipolar transistor different from a MOSFET is that a bipolar transistor is a current-controlled device and a MOSFET is a voltage-controlled device. Well, not really. A current does flow when we forward bias the base emitter junction. And it turns out that in practice, in the use of bipolar transistors, it is frequently easier to control the current than it is to control the voltage. Because notice, the currents depend exponentially on the forward bias. So it would be very sensitive to the voltage that we apply to the base emitter terminal. We can get much better control by saying if we control the current that we inject in, then the voltage that we want is going to be proportional to the log of that base current. And that means it's much easier to set that forward bias precisely where we want to when we can set it by injecting a current instead of a voltage. But the device is still operating by forward biasing and energy barrier and lowering that energy barrier for electron injection. This current gain is an important figure of merit for a bipolar transistor. We would like the base current to be as small as possible. We use it to control the forward bias, but we really, that is a parasitic current that we prefer not to have. We have expressions for the collector current and the base current, both due to forward bias injection of carriers. We simply divide the two, and we'll get an expression for their ratio, which we call beta. And the ratio will depend on the ratio of diffusion coefficients, on widths of the regions over which the carriers are diffusing, doping densities of the two regions, and the Ni squared, the intrinsic carrier density in the N and the P region. So that ratio we call beta. In general, we'd like that to be high. We can make use of it in circuits as long as it's on the order of at least 10, 20, 30 or so. Okay. So in the forward active region, which is like the saturation region of a MOSFET, a key quantity will be the beta of this transistor. We can use this in useful applications if the beta is high enough, and we have a simple expression that relates beta to the parameters of the semiconductor that we can control, the doping density, the thickness, and to the diffusion coefficients and intrinsic carrier densities, which we have to live with. They're material properties of the material that we're using. The IV characteristics will have output characteristics. Output current is the collector current. Output voltage is the voltage between the collector and the emitter, just like the output characteristics of the MOSFET. In fact, they look a lot like the output characteristics of a MOSFET. But now, instead of stepping up the base emitter voltage, we're stepping up the current. Each one of these lines refers to a different current injected into the base contact. There'll be a region here that we call the forward active region. Emitter base junction is forward biased. Base collector junction is reverse biased. Like the saturation region of a MOSFET, in that region, we talk about beta, the ratio of the collector to the base currents. We can also plot the transfer characteristics. We can do that on a log plot, the log of the output current versus the input voltage. So just like the transfer characteristics of a MOSFET. We'll see a subthreshold regime. Because there is no volt drop lost in an oxide when we apply the voltage directly to the PN junction, the subthreshold swing is always 60 millivolts per decade. So we'll have a base current that is 10, 20, 30 times lower than the collector current. If we go to high enough current densities, we'll see that the current rolls over. That sort of looks like the above threshold region of a MOSFET, but it's not. This device is really operating in the subthreshold or the 60 millivolt per decade regime over the entire range of currents. What's happening up here is when we get to very high currents, we have volt drops in these series resistances that are reducing the voltage that actually gets in and forward biases the PN junction. So that rollover that you see there is just due to the inevitable effects of the series resistances that are there. Now, let's compare MOSFETs versus bipolars. We have two different types of transistors. How do they compare? We've seen that for analog or RF applications, we have two important figures of merit. One is the transconductance, the derivative of output current with respect to input voltage. The other is the gain bandwidth product, the maximum frequency at which we get a gain of at least 1. And that's the ratio of transconductance over 2 pi times the total capacitance of the device. Now, in a MOSFET, in the velocity saturated mode, the drain current is given by a set of constants times VGS minus threshold voltage. In the bipolar transistor, the behavior is exponential due to this exponential injection of electrons across the emitter base energy barrier. So it's proportional to E to the Q voltage between the base and the emitter over KT. Transconductance, we just differentiate output current with respect to input voltage. The transconductance of the MOSFET is just these set of constants, oxide capacitance, saturation velocity, things like that. I can rewrite that expression as output current divided by VGS minus thermal voltage. That's just another way of writing the same quantity. Bipolar transistor, I can differentiate its output current with respect to its input voltage. And what I find in this case is I just bring down a KT over Q downstairs. So I can write the transconductance as output current, collector current, divided by a voltage. In this case, the voltage is KT over Q. All right, that's the bottom line. Let's take a look at that. We have these two different expressions for the transconductance of these two different devices that operate on similar physical principles. Let's just assume that I'm biasing at 1 milliamp. It won't really matter. I typically might have in a MOSFET a gate to source voltage of 1 volt and maybe a threshold voltage of 0.2 of a volt. For the bipolar transistor, I'll be operating at room temperature. KT over Q is 0.026 volts, a much smaller voltage. If I compute the transconductance of the MOSFET, that's 1 milliamp divided by VGS minus VT, that's about 2.5 millisiemens. If I compute the transconductance of the bipolar transistor, you can see that it is 1 milliamp divided by a much smaller voltage, so it's more like 40 millisiemens. So if we compare those two, you can see that the transconductance of the bipolar transistor is significantly larger than the transconductance of the MOSFET by a factor of 20 or so. So this is the key difference, that in practice, MOSFETs display a significantly higher transconductance. They are inherently better amplifying devices. Okay. Now, I also want to point out that in bipolar transistors, series resistance is a significant problem. If we look at FT, FT is the ratio of transconductance over 2 pi times total capacitance. MOSFETs have much lower transconductance, but they also have much lower capacitance. Bipolars have much higher transconductance, but they tend to have much higher capacitances as well. The way that we get high FTs from bipolar transistors is we operate them under very high current levels. You can see why here. If I look at G sub m over total capacitance, I can write that 2 pi FT. This is 1 over some characteristic time, delay time. So if I look at my delay time, I can write my delay time as the total capacitance divided by Gm. The total capacitance consists of two components. There is an intrinsic component due to the capacitance of the emitter-base junction. And there is a parasitic capacitance due to the inevitable stray fields that will give me parasitic capacitances between the base terminal and the collector and other leads. Okay. Now, if I want to look at the intrinsic capacitance divided by the transconductance, the definition of capacitance is derivative of charge with respect to voltage. The definition of transconductance is derivative of current with respect to voltage. Current is charge divided by time. So if you look at this expression, you can see that what we have here is the intrinsic transit time of the device. This is basically the time it takes an electron to move from the emitter across the base and out to collector, right? The inherent transit time limitation of the speed. Now, There is also a G sub M, AC parasitic over G sub M. That's going to give additional delay. But G sub M is collector current divided by KT over Q. If I make the collector current large enough, I can make this extra component due to the parasitic capacitance small, and I can get high speed by making that negligible. That is the reason that for high frequency operation, we run bipolar transistors at very high current densities to try to reduce the effect of those parasitic capacitances. Okay, so to summarize, BJTs are superior RF and analog devices because they have much higher transconductance, but both devices can achieve high FTs. The MOSFET because it has low parasitic capacitance, the bipolar transistor because it has high transconductance, and we can minimize the effect of parasitic capacitances. The key difference then is that bipolar transistors offer much higher transconductances, which is going to give us much higher drive currents in these devices. When we need a lot of current, so we need a lot of RF power, the bipolar transistor will be the device that is most suitable. Now, the personal electronics that we carry around has billions and billions of silicon MOSFETs, but it also has a few other devices. There may be some transistors for power management. We've talked about power MOSFETs. But there are also some devices for the wireless communication that we have in most of our personal electronic devices. Many of these products, in fact almost all of them, will use a device called a silicon germanium heterojunction bipolar transistor. So there may be billions of MOSFETs to do what we need to do in terms of digital signal processing, but there has to be one HBT in order to do the wireless communication properly. So the bipolar transistors, there may be a small number of them, but they can be very important. Well, what is an HBT? That's what we want to talk about in the rest of this lecture. Modern transistors are all heterojunction bipolar transistors, so I want to explain what an HBT is, why they are useful, and we can do that by going back to this simple expression for the common emitter current gain that we developed. If we look at that, we see a ratio of intrinsic carrier concentrations in the base to that in the emitter. If we have a material made out of all the same semiconductor, we would call that a homojunction bipolar junction transistor. Then the NIs are the same and that term drops out. So you can see that the only way that we can get high current gain is really to dope the emitter much more heavily than the base. That will give us high current gain. Now, we would prefer to dope the base very, very heavily. That would make it thin, and we could still maintain the resistance as low. We need low resistance because that plays an important role in RF circuits. So we would like to have a very thin base for speed. We would like it to be very heavily doped to lower its resistance. But we are constrained by homojunction physics to make the doping of the emitter much more heavily than the doping of the base in order to suppress that back injection of holes. But we can get around that. If we use a wide bandgap emitter, then we're recalling that the intrinsic carrier concentration squared goes as e to the bandgap over kT, e to the minus bandgap over kT. If we have a wide bandgap emitter, we have the ratio of the intrinsic carrier concentration squared, assuming that the effective densities of states are about the same, gives us an e to the difference in bandgap over kT. That number, just for a small bandgap difference of a 2 or 3/10 of an electron volt, can give us an enormous number that will offset this ratio here of doping densities. We can, in fact, make the base much more heavily doped than the emitter and still get acceptable current gain. That is the primary advantage of an HBT. Sometimes, you'll see, oftentimes we use a double HBT. One of the things that a double HBT gives us is a more symmetrical device, which is often useful. It can give us a reduced collector offset voltage, which I'll explain in a minute. And the fact that it's a wider bandgap means that we can often apply a reasonable voltage and still get a high enough breakdown voltage because it's a wider bandgap material. All right. Okay, so if you would like sort of a look at current state-of-the-art in 3.5 HBT technology, I can refer you to the first reference here. And if you'd like an understanding of the critical role that parasitics play in achieving high-frequency performance in these devices, there's a second paper that I can refer you to. This is what the output characteristics might look like for modern-day 3.5 HBT technology. One of the things that you'll notice is that the current doesn't go through the origin. There is a collector-emitter offset voltage, which is undesirable because it increases the power dissipation. The use of a double heterojunction bipolar transistor sort of reduces that offset voltage somewhat. But the structures that are built are still somewhat asymmetrical, so that it's not a symmetrical device, and that leads to that offset voltage, which you're not used to seeing, certainly not in a MOSFET, which can be almost exactly symmetrical. You'll see that there is no early effect. It's being masked by thermal effects. These devices are run at very high current densities. There's a lot of self-heating. Their thermal conductivity doesn't tend to be as high as silicon. Those thermal effects can lead to a reduction of current as you go to higher and higher voltages and you have more power dissipation. So those are what the IV characteristics look like. These are an example of FT and Fmax versus the DC bias currents. And you can see that as you increase the bias current higher and higher, you get higher and higher frequencies. Eventually it goes too high and the series resistance and thermal effects dominate and you reach a peak. You can see that the peak Fmaxes here are exceeding a terahertz for this device. So very, very high frequencies can be obtained if we run these devices at very high current densities to minimize the influence of parasitics. These devices are also created with very sophisticated epitaxial growth techniques. So these are more expensive than general silicon manufacturing techniques, but what they give us is exceptional RF performance when we need that. This particular device has a wide bandgap indium phosphide emitter, a smaller bandgap indium gallium arsenide base layer, a wider bandgap collector. There's a graded layer between the base and the collector, such that there isn't a discontinuity here that traps electrons in the base that allows them to more smoothly flow out the collector. The collector is wide bandgap, which gives us then a more symmetrical device that also has a higher breakdown voltage than we would get if we used in-gas for the collector as well. So that's an example of what it might look like. The fabrication processes tend to be simpler than silicon processes. A typical process might look like this. So the first step in the process would be, after growing the layers and depositing the emitter metal, would be to do an etch. After the emitter, we first do the emitter metal deposition. Then we do an emitter etch. We etch down through the emitter and we expose the base. Then we can evaporate the base metal contact. We can then do a second etch. We can etch away through the base and expose the collector areas. Then we can deposit the collector contacts. The heart of our device then is this one-dimensional structure, but again, the current has to get out through the contacts, so there's lateral 2- and 3-dimensional current flow. So if I think about these 3.5 indium phosphide HBTs, some of the key challenges are the contact resistivity, because we operate them at very high current densities. That leads to some device heating issues, so we have to be carefully consider the thermal effects in these devices. Parasitic capacitance are a constant struggle to minimize the effects of these parasitic capacitances so that we can push to the higher and higher frequencies. And current gain is a bit of a problem, because as we reduce the size of the device, then around the perimeter there are some defects that occur in this mesa isolation process. The injected electrons can recombine with holes at those surfaces, and that lowers the current gain of the device. All right, so let's just summarize. This has been a quick look at HBTs so that we know what the devices are about, how they operate, and what they are useful for. They're an important device for high-frequency applications, especially high-frequency power applications where they're even better than HEMPs. silicon germanium HBT technology, which I haven't been able to say very much about, but they are also HBTs built on a silicon germanium material system. Germanium is a smaller band gap than silicon, so that gives us our wide and narrow band gap layers. They're a critical technology widely used in personal communication, personal electronic wireless communications for those devices. HBTs and HEMTs offer similar maximum frequencies of operation in the terahertz regime these days, but compared to HEMTs, HBTs have much higher transconductance and therefore can deliver higher power to those applications where we need it. But the takeaway line here is that the HBT is not a fundamentally different device than the silicon MOSFET than we've learned to understand. It is a barrier-controlled device. We are just accessing the barrier and modulating it directly with our base emitter voltage rather than indirectly through a metal oxide semiconductor structure. So that's a quick look at HBTs. We've covered a lot of topics in this unit. The next topic that I would like to revisit is the topic of compact models. Whatever type of transistor we're developing or using in applications, we need a good compact model to design circuits. And we briefly discussed this in Unit 1. I'd like to revisit compact models briefly now that we know more about transistors and say a few more words about compact models for circuit design. That'll be our topic for the next lecture.